Sometimes we really do take the basics for granted. Like we think we've got it all figured out.
Right.
But today on this deep dive, we're going back to the very, very beginning.
Yeah.
The bedrock, almost.
Just the foundation.
Yeah, the foundation of math.
Exactly.
Addition and subtraction.
It all starts there, right?
I mean,
it does.
It really does.
But, you might be thinking, okay, addition and subtraction. I did that in grade school.
Been there, done that.
Yeah, I've moved on to bigger and better things.
Right. Yeah.
Stick with us because we're going to go deeper.
We are.
Than just the how-to.
We're going beyond the simple how-to.
We're going to the why.
Yeah.
And really exploring how these seemingly simple operations are kind of the unsung heroes of math.
They are.
They're quietly powering so much of our daily lives.
Well, and I think that's what we're hoping to really uncover in this deep dive,
Yeah. We've got this really fascinating collection of insights and examples that we're excited to unpack with you.
Yeah.
And the goal is for you to not just remember, okay, how to add and subtract.
Right.
But to really grasp the fundamental principles that are at play here and see how deeply woven they are into the fabric of our everyday experiences.
Yeah.
It's about gaining a richer appreciation for these foundational tools.
Yeah, for sure.
Yeah.
Okay, well, let's dive right in
Right.
with addition.
Sounds good.
At its core, what's the fundamental idea? Like, what's really happening when we add?
So put simply, addition is the process of combining quantities or increasing in amount. It's about finding the total or the sum when you bring two or more sets together.
Okay.
So think of it as the fundamental operation for building things up numerically.
Yeah, so it's like taking separate piles and making one bigger pile.
Exactly.
Yeah.
Okay.
And we've got that universal symbol, the plus sign, that signals this joining action.
The plus sign.
But the numbers themselves have names too, don't they?
They do. The numbers being combined, those are called add-ins.
Add-ins.
And the resulting value, that's the sum.
The sum.
Or the total.
Okay.
So add-ins come together to create a sum.
Okay, so to get like a clearer picture, let's look at an example.
Yeah.
Like what can our sources offer us to sort of visualize addition in action?
Okay, imagine that you have a collection of 2 yellow stars.
Okay.
And then you come across another group of 3 purple stars to find the total number of stars that you have.
Yeah.
You perform addition 2 plus 3.
Yeah.
Which results in a sum of 5 stars.
5 stars.
It's basic aggregation of distinct groups into a single larger one.
Right.
Yeah.
I've always found the number line to be a really intuitive way to picture math concepts.
Yeah, the number line is fantastic.
Yeah.
It offers this great visual representation.
Yeah.
So if you start at a particular number, say 10, and you want to add 3, you simply make 3 jumps to the right along that line.
Yeah.
With each jump representing 1 unit being added.
Okay.
And so you'll land on 13.
13.
Clearly illustrating that 10 plus 3 equals 13.
Yeah. Yeah.
Yeah.
And then to bring it firmly into the real world, our sources point to something we all encounter.
Okay.
Apples.
Apples. Consider this. You have 5 apples in a basket.
Okay.
And you add 2 more apples to it. So the physical result is that you now have 7 apples.
7 apples.
It's the same underlying principle of combining quantities.
Yeah.
Just applied to tangible objects.
Right.
Yeah.
So addition is fundamentally about joining and increasing.
Yeah.
But it's not just a free-for-all. There are some really interesting properties that govern how it works.
Absolutely.
Right.
These amazing properties of addition, as our sources highlight, they give addition a remarkable flexibility.
Yeah.
And make it much easier to manipulate and understand.
Okay. First up is the commutative property.
Oh, okay.
It sounds kind of formal.
Yeah, it does a little bit.
What's the everyday takeaway of this property?
So in essence, the commutative property tells us that the order in which you add numbers doesn't affect the final sum.
Okay.
So whether you calculate A plus B or B plus A, the result will be the same.
Okay.
And this is incredibly useful in mental math, as you can often rearrange numbers to make them easier to add.
Right.
It also touches on the idea that when you're combining sets, the order in which you combine them doesn't change the final collection.
So 4 plus 2 gives me 6.
Yes.
And clipping it to 2 plus 4 still results in 6.
Exactly.
The order is irrelevant to the outcome.
Precisely.
Okay.
Our sources use a great analogy here.
Okay.
If you have 3 red apples and then get 2 oranges, you end up with 5 pieces of fruit.
Right.
Whether you receive the apples first or the oranges first, the total number of fruits remains the same.
Okay.
It's about the final collection, not the sequence of addition.
I like that analogy. That really grounds it.
Yeah.
Okay.
Yeah.
Next up is the associative property.
Okay.
Another impressive sounding term.
Another one.
What's the core idea behind this one?
Okay, so the associative property deals with how we group numbers when we are adding 3 or more of them.
Okay.
And it states that the way you use parentheses to group the addends doesn't change the final sum.
Okay.
So A plus B plus C in parentheses will always equal A plus B plus C in parentheses, but grouped differently. This property becomes vital when dealing with longer strings of additions because it allows you to group numbers in the most convenient way.
Gotcha.
It hints at how larger sums can be broken down into smaller, more manageable steps.
Okay, so let's unpack that.
Okay.
If I have 2 plus 3 plus 4, I could first add 2 plus 3 to get 5 and then add 4 to get 9.
That's right.
Or I could add 3 plus 4 to get 7 and then add 2 to get 9.
Exactly.
So the grouping changed, but the final sum remained the same.
Exactly. The sources illustrate this with blocks.
Okay.
2 red, 3 blue, and 4 green blocks total 9. Regardless of whether you first count the red and blue together or the blue and green together.
Yeah.
The association or grouping doesn't alter the total.
So these properties, while seemingly basic, actually provide a powerful flexibility.
Yeah, they do.
In how we approach addition.
Absolutely.
Okay. Yeah. Now let's shift gears to its counterpart, subtraction.
All right.
What's the fundamental concept here?
Okay.
What are we really doing when we subtract?
So subtraction is the operation of taking away a quantity from another.
Okay.
Or determining the difference between 2 quantities. It answers the questions how many are left.
Yeah.
Or what is the difference in size between 2 amounts.
Okay.
It's the fundamental operation for reducing a numerical value.
Okay. And just like addition has its plus sign, subtraction is signaled by the minus sign.
Just minus sign.
And the components of a subtraction problem also have specific names, don't they?
They do.
Okay.
So the initial number you're subtracting from is called the minuend.
Minuend.
The number you are taking away is the subtrahend.
It's a subtrahend.
And the resulting value, that's the difference.
The difference.
So minuend minus subtrahend equals difference.
Okay.
Yeah.
Minuend subtrahend difference.
There you go.
Got it.
Yeah.
So if we start with 9 cupcakes, the minuend and 7 are eaten.
Okay.
The subtrahend.
Yes.
The 2 remaining cupcakes are the difference.
Precisely.
Okay.
And just like with addition, we can visualize subtraction on a number line as well.
Okay. How does that work?
So if you begin at 9 and you want to subtract 4, you move 4 steps to the left.
Okay. To the left this time.
To the left this time.
Okay.
Along the number line.
Yeah.
And you land on 5.
5.
This visually demonstrates that 9 minus 4 equals 5.
Okay.
Yeah.
And our sources provide another relatable example.
Okay.
This time involving giving away red apples.
Okay, so imagine you begin with 5 red apples.
Okay.
That's your minuend.
Minuend.
And you decide to give 3 away to a friend.
Okay.
That's your subtrahend.
Subtrahend.
You are then left with 2 apples.
Yeah.
That is the difference.
Okay.
This is subtraction in a tangible, real-world context.
Okay, now here's where the relationship between these two operations gets really interesting.
It does.
Addition and subtraction don't exist in isolation, do they?
They do not.
They're actually deeply connected.
They are indeed.
Right.
They are, in fact, what are called inverse operations.
Inverse operations.
Which means that one operation can undo the effect of the other.
Okay.
This inverse relationship is a cornerstone of arithmetic. And it has significant implications when we move into more advanced mathematics.
Okay.
Like solving equations.
So if I perform an addition, I can use subtraction to get back to my original number.
Exactly.
Okay.
Yeah.
Our sources highlight this perfectly with 3 plus 5 equals 8.
Yes.
And 8 minus 5 equals 3.
Right.
They effectively cancel each other out.
Exactly. And it works in reverse as well.
Okay.
So if you start with 8 minus 5 equals 3, you can use addition to return to the original number.
Okay.
3 plus 5 equals 8.
Right.
This bidirectional undoing
is
what makes them inverse operations.
Okay. And this leads us to the concept of fact families. It sounds like something you'd find in a math textbook.
Yeah, it does.
but it's actually a really useful way to think about this relationship.
Right.
Isn't it?
It is.
Okay.
So a fact family is simply a collection of related addition and subtraction equations that use the same three numbers. For example, with the numbers 3, 4, and 7, you can form these four facts. 3 plus 4 equals 7.
Yeah.
4 plus 3 equals 7.
Okay.
7 minus 3 equals 4.
Gotcha.
And 7 minus 4 equals 3.
Okay.
Recognizing these patterns can significantly speed up problem solving.
So understanding these fact families can actually be a shortcut
Absolutely.
for solving problems.
It can be.
Okay.
Yeah.
So if you encounter a subtraction problem like 15 minus 9 equals question mark, you can reframe it in your mind using the inverse relationship as an addition problem.
That's right.
9 plus question mark equals 15.
Exactly.
And if you recall that 9 plus 6 equals 15, then you immediately know that 15 minus 9 equals 6.
Precisely.
Okay.
Utilizing this inverse relationship is a valuable strategy for tackling subtraction.
Gotcha.
Yeah.
Okay, so we've covered the foundational ideas.
Right.
But what happens when we start working with larger numbers,
Right.
multi-digit addition? It's not quite as straightforward as counting on our fingers anymore?
No, it's not.
Right.
That's where organization and a systematic approach become really essential.
Yeah.
So when you're adding numbers with multiple digits, the crucial step is to align them correctly.
Okay.
According to their place value.
Place value.
Ones under tens, hundreds under hundreds, and so forth.
Right.
This ensures that you're adding comparable units together.
Okay, and why is this precise alignment so critical?
Well, because you are essentially summing the contributions
Yeah.
from each place value column independently.
Right.
Adding tens to ones would lead to a nonsensical result.
Yeah.
By aligning them, you treat each column as a separate addition problem.
Gotcha.
And then handle any necessary regrouping between the columns.
Oh.
You start the addition process from the rightmost column,
Okay.
which represents the ones place.
Yeah.
Yeah.
Now, what happens if the sum of the digits in a particular column is 10 or greater?
Okay.
That's where the concept of carrying over comes into play.
It does.
Right?
It does.
Can you explain what's happening there?
Yes. So when the sum of the digits in a column is 10 or more,
Yeah.
you write down the digit. That represents the ones place of that sum, the answer for that column.
Okay.
The digit in the tens place of the sum is then carried over to the next column to the left.
Okay.
This carried over digit represents a group of 10 from the previous place value being added to the next higher place value.
Essentially regrouping 10 ones as 110.
Yeah.
Or 10 tens as 100 and so on.
Right.
Yeah.
Our sources provide an example.
Okay.
234 plus 187.
Right.
Could you walk us through the carryover process in this specific instance?
Certainly. So we begin by aligning the numbers.
Okay.
234 stacked above 187, starting with the ones column.
Yeah.
We have 4 plus 7, which equals 11.
11.
So we write down the one in the ones place of our answer.
Okay.
And carry over the one, representing 1. 10,
Yeah.
the tens column.
The tens column.
Moving to the tens column.
Okay.
We now add the digits, including the carryover.
Right.
So 1 carried over plus 3 plus 8
Equals 12.
equals 12.
Okay.
So we write down the 2 in the tens place of the answer and carry over the 1, representing 100 to the hundreds column.
Hundreds column. Finally, in the hundreds column, we add the digits, including the carryover.
Right.
1 carried over plus 2 plus 1 equals 4. Therefore, the final sum is 421.
Okay.
Yeah.
So seeing that one physically moved to the next column really clarifies why we carry over.
I think so.
Okay.
Yeah.
Now, what about subtracting larger numbers?
Okay.
Multi-digit subtraction.
Multi-digit subtraction.
Is the principle of aligning by place value equally important?
Absolutely.
Okay.
Just as with addition.
Yeah.
Maintaining the correct place value alignment is crucial for accurate multi-digit subtraction.
Okay.
So you write the minuend above the Sugrahand,
Right.
ensuring that The ones 10, hundreds, and other place values are aligned vertically.
Yeah.
And you begin the subtraction from the rightmost column.
Okay.
The ones place.
Right. And what do we do when the digit on top in a column is smaller than the digit on the bottom?
Okay.
We can't directly subtract a larger number from a smaller one.
Exactly.
That's where borrowing comes into play.
That's where borrowing comes in.
What's the mechanism behind borrowing?
Okay, so when the top digit in a column is smaller than the bottom digit, we need to borrow from the column immediately to the left.
Okay.
Borrowing one from the tens place, for example, means taking one group of 10 and converting it into 10 ones, which are then added to the ones place of the minuend. The digit you borrowed from in the column to the left decreases by 1.
Okay.
This is another form of regrouping where we exchange a unit of a higher place value for 10 units of the next lower place value.
Okay. Could you illustrate this borrowing process?
Sure.
Using the example from our sources.
Okay.
412 minus 256.
Okay, so we align the numbers. 412 over 256, starting with the ones place. We need to subtract 6 from 2, which we can't do directly.
Right.
So we borrow 110 from the tens place in 412.
Okay.
So the 1 becomes a 0. That borrowed 10 is then added to the 2 in the ones place, making it 12.
12.
Now we can subtract 12 minus 6 equals 6.
6.
Moving to the tens place, we now have 0 minus 5, which we also can't do.
Can't do.
So we borrow 100 from the hundreds place.
Right.
The 4 becomes a 3.
Okay.
That borrowed 100 is converted into 10 tens, which are added to the 0 tens, making it 10.
10.
Now we subtract 10 minus 5 equals 5.
5.
Finally, in the hundreds place, we have 3 minus 2 equals 1.
1.
Therefore, the difference is 156.
Okay.
Yeah.
That step-by-step explanation really demystifies the borrowing process.
I hope so.
It's a clever way of rearranging quantities.
It is.
To make the subtraction possible within each place, value. Okay, now let's introduce decimals into the mix.
Okay.
That little dot changes things a bit, doesn't it? When we're adding and subtracting.
It does.
Oh, yeah.
While the presence of the decimal point adds this visual element, the fundamental principle of organization remains paramount.
Okay.
So the most critical rule when adding or subtracting decimal is to ensure that you always align the decimal points vertically.
Okay.
This ensures that you are adding or subtracting digits
that
represent the same place value.
Okay.
Tenths with tenths, hundredths with hundredths, and so on.
Right.
Yeah.
And why is this vertical alignment of the decimal points so crucial?
Well, because the decimal point acts as a marker.
Okay.
Separating the whole number part from the fractional part of the number.
Okay.
Aligning the decimal points ensures that you are operating on corresponding fractions.
Gotcha.
Tenths with tenths, hundredths with hundredths, and whole numbers correctly.
Right.
As our sources mentioned, it's sometimes helpful to add trailing zeros
to
the end of a decimal so that both numbers have the same number of decimal places.
Right.
This doesn't change the value of the number, but it aids in visual alignment.
Right.
Yeah.
So if we're adding 3.45 plus 1.2, we would rewrite 1.2 as 1.20.
Yes.
Aligning the decimal points and the hundredths place.
Correct.
And then proceed with addition.
Right.
Just as we would with whole numbers.
Exactly.
Making sure to place the decimal point in the sum directly below the aligned decimal point.
Precisely. So adding 3.45 and 1.20 results in 4.65.
4.65.
With the decimal point maintained in its vertical position, the same logic applies to subtraction. So if you have 5.6 minus 2.15, you would rewrite 5.6 as 5.60.
Right. Add that trailing zero.
Add that trailing zero. Then perform the subtraction. And the decimal point in the difference, 3.45.
3.45.
Will also be aligned.
Okay.
Yeah.
So the alignment of decimal points seems to be the key.
It is the key.
Okay. Now let's move on to fractions.
Okay.
They have a numerator and a denominator.
Right.
How does addition and subtraction work with these?
Okay.
At least when they share a common denominator?
Okay, so when fractions have the same denominator, it signifies that you're dealing with parts of a whole that are of equal size.
Okay.
This common base makes addition and subtraction straightforward.
Okay.
The denominator indicates the total number of equal parts in the whole.
Right.
Yeah.
So if we're adding fractions with a common denominator, what do we do with the numerators and the denominator?
You simply add the numerators together.
Okay.
And keep the denominator the same.
Okay.
So, for instance, if you have 1/4 plus 2/4, you add the numerators. Yeah. 1 plus 2 equals 3.
3.
And retain the denominator 4, resulting in 3/4.
3/4.
Think of it like adding slices of a pie.
Yeah.
1 slice plus 2 more slices of the same size pieces.
Right.
Gives you 3 slices in total.
Okay, that's a great way to visualize it.
Yeah.
And subtraction with common denominators works in a similar fashion.
Exactly. When subtracting fractions with a common denominator, you subtract the numerators and keep the denominator unchanged.
Okay.
So, for example, if you have 3/5 minus 1/5, you subtract the numerators.
3 minus 1 is 2.
3 minus 1 equals 2.
Okay.
And keep the denominator 5.
Okay.
Resulting in 2/5.
2/5.
It's like having 3 pieces of cake out of 5. And if you eat 1, you are left with 2 pieces out of 5.
Okay.
Yeah.
Our sources briefly mention that if fractions have different denominators, we first need to find a common denominator before we can add or subtract them.
We do.
That sounds like
it is
a more involved process.
It is a bit more involved.
That we can perhaps explore in a future deep dive.
Absolutely.
Yeah.
Dealing with different denominators requires finding equivalent fractions that share a common denominator so that you can then add or subtract parts of the same size.
Right, parts of the same size.
Yeah.
Gotcha.
Yeah.
All right, so we've explored the mechanics of addition and subtraction. Yeah. But as we touched on at the beginning, these aren't just abstract exercises.
No.
Where do these operations actually manifest in our daily lives?
Well, the applications are truly ubiquitous.
Okay.
Consider managing money.
Okay.
You use addition to calculate the total cost of your purchases and subtraction to determine the amount of change you should receive.
Absolutely. So if I pick out an $8 toy and a $5 book, I need to add those amounts to know I owe $13.
That's right.
And if I pay with a $20 bill, the cashier uses subtraction to calculate my $7 change.
Exactly. Time management is another significant area. Figuring out the duration until a scheduled event or the total time spent on various activities relies heavily on subtraction and addition.
Right.
If your practice starts at 5 p.m.
and
it's currently 3 p.m., you subtract to find you have 2 hours until practice.
2 hours.
Similarly, if you spend 30 minutes on homework and 45 minutes playing, you add those times to find a total of 75 minutes.
Right.
Yeah.
And the culinary world is full of it.
It is.
Cooking and baking involve precise measurements of ingredients.
They do.
Often requiring addition to combine amounts.
Yes.
And sometimes subtraction if you need to adjust a recipe.
Exactly.
So if a recipe calls for 2 cups of flour and you only have 1, you subtract, figure out you need 1 more cup.
That's right.
Okay.
Measurement in general.
Yeah.
Whether it's for cooking home improvement or even